Here it is. The so the definition right here. Any thoughts about congruency, or which we know that congruency is an equivalence relation, but then as we talked about last time, you can combine right there in the middle two congruencies together in hope of creating a new equivalence relation. So any thoughts about this? Hope you think some more about it, because yeah, it is an interesting problem. It really takes you to the next level. Well, actually, the next level will be really it will be actually what happens if you combine two equivalence relations in that manner. Will it be still an equivalence relation? Okay, so that would be really purely abstract and question rather than something more specific, which when it's about numbers, it's kind of a less. So we're talking about here, equivalence relation is might be the first topic is of mathematics that is kind of mathematics for mathematicians. You know, when it is truly abstract and does not refer to anything even remotely specific. But at the same time, as you can see, there are so many examples of mathematics or outside that provide us with that with examples. So whenever we prove about equivalence relations, we prove that about all the equivalence relations at the same time. Okay, so and that's what the last theorem is about. So let's take another look at it. So it's about equivalence classes, all elements equivalent to that to a particular value. Okay. So before we go into the theorem, let's maybe what's missing a little bit more examples of equivalence classes. The only equivalence class I pointed out over there is that when it is equivalence class of a congruent number modulo 3, these you just go three at a time, and you'll get that will be your equivalence class, and there and then so that's one equivalence class. You can easily list them. So 0 equivalent to 3 equivalent to 6. So these are divisible by 3 equivalent to 9. And so on. Okay, so and then the next one in the next line divisible remainder is 1, and the next one remainder is 2, right? So it will be 2 equivalent to 5 equivalent to 8 equivalent to 11 and so on. Okay, so that's how we have these are the 3 equivalence classes. You can count them as numbers, integers modulo 3. 3 equivalence classes. You can point them out explicitly, even though the definition of congruency is equivalence relation. So all you say is that these two elements are related when they have the same or equivalent, when they have the same remainder. Then you keep stick with analysis, and then that's what comes out of that analysis is that is equivalence classes to begin with. So these are the 3 equivalence classes, and in general you realize there will be, if it is modulo n integers, then there will be n equivalence classes. Okay, so let me go here. So modulo n integers. Okay, and so question would how many equivalence classes? The answer is n. Okay, and then not just that, you can point out what they are. Okay, in fact we know how it is based on the remainder theorem, right? So by the remainder theorem, every x integer will be represented as nq plus r, and r between 0 and n. So these are n possible remainders. Then there will be exactly one equivalence class for each. Okay, so you can be specific. So so equivalence class of in fact, the smart way of writing them up is to write up one equivalence class per remainder rather than picking a random number. Let's just take the numbers between 1 and n, 0 and n minus 1. Okay, so 0 equivalence class of 0. So all x congruent to 0 mod n. Okay, then 1 all x congruent to 1 mod n, and so on. N minus 1 congruent, all of those x's that congruent to n minus 1 mod n. And then it seems like I'm going to continue and say that n is equal to those integers congruent to n mod n. But I don't do the that line is pointless because just let's compute what that is. So, well, what is the set? All the numbers that have the same remainder as n under division by n. What are we talking about? What numbers have the same remainder under division by n as n? What is the remainder of n when divided by n? 0. So what can you say about the set then? With 0 remainders. In other words, it's already at the top of the list. So it is simply 0. So I don't really want to put it on the list because it is redundant. And if I can try to continue on in that fashion, I will be running into pretty much the same problem. Same remainder, x is same remainder as n plus 1 mod n. What does it mean? It's simply the same as what? Okay? And so you go on to infinity, and that is pointless. You start repeating yourself infinity many times. I could even go backwards. I could have equivalence class of -1. What it is x equivalent to -1 mod n. And once again, what is so special about that? What's equivalence class of -1? What's the remainder of -1 when you divide by n? Well, look at the remainder theorem right here. Try to put x -1. What do you get? -1 is equal to nq plus r, and the q and r are the ones that we need to find.
1 over n.
No, not 1 over n. No, what is the no. Well, remember that, well, let me move. nq plus r n plus 1, and this is 0. Okay, does this help?
R plus 1 divided by -q? Or negative?
No, I'm not. Look at this expression. So on the left I have 0. On the right I have r plus 1. Okay, so the right hand side, the left hand side is 0, which means that the right hand side is also 0, which means both of them are divisible by n, which means that this is divisible by n. But r is between 0 and n. So, what is r? R is less than n, yet r plus 1 is divisible by n. No. 0, you end up with 1.
Would it be all the numbers?
What? No, just, what? Almost. If r is equal to n, well, first of all, it cannot be equal to n because it has to be less than n, right? And secondly, well, it doesn't, n minus 1. The answer is n minus 1. So n minus 1 plus 1 gives you n. It is divisible by n, and that is the answer. Okay, so in -1, the remainder of -1 divided by n is in fact n minus 1. Why? Because the remainder has got to be positive. Okay, n is between 0 and n. So that's why you kind of push it in the opposite direction. So like I said, n minus 1. Okay, so that is the repetitiveness that is goes on in both directions. Only the two that we care, only the block that we care about is this. These are we could pick any block. Any block would give you all the, in this list, I could pick any block of n, and it will give me all the equivalence classes, such as, well, this is another one, like this one. This is also, all equivalence classes are here. You can check it out. All the equivalence classes are there. It is just a point of what is the most prudent way to choose representative of the equivalence classes. So equivalence classes are repeating themselves, but which one? You pick the smallest one, the one that corresponds directly to the remainders. So why go beyond n minus 1 or below 0 when you can have just between 0 and n minus 1, and these are the n plus n equivalence classes. They're listed right here. Okay, so they are listed. And so which pretty much closes the subject here. Well, what else is there? We have our equivalence classes specifically written. They have been represented in a kind of a unique way. So like I said, at the bottom you can see how the different equivalent classes seemingly, different representatives give you the same equivalence class. So yeah, I can pick n or I can pick 0. It's the same equivalence class. N plus 1 or 1, it's the same equivalence class. Okay, so if we want to keep it straight, we compact, and so that we after all we have finitely many equivalence classes. So you don't want to go into infinity if we have only finitely many. So that is the best way to write up the equivalence classes is that what I have in the purple box. Okay, violet. Okay, so that's one list of classes. Let's go over these examples and see more over the examples of equivalence relations, and once again examine the equivalence classes. Okay, so we have one for congruences. That is, the problem is solved. Now let's go from the top here. This is the definition. This is the first example. So this is the trivial equivalence class. When x is equivalent to y, only when x is equal to itself. What are the equivalence classes? Equivalence class of x is all the elements equivalent to it, but it is only equivalent to itself. So what's the equivalence class? X. This is how we write it. So set with only one element present, that you will put braces, right? On the left is the notation for the equivalence class. Okay, on the right we have just a list of all elements equivalent to it. Okay, so that's one way to do it. Now, so the second example here is the equivalency statements. It's pretty hard to list all possible statements that are equivalent to one particular statement. Now, next example is not. This one is transparent. What are all the equivalence classes? You can see one equivalence class right there. Here's another equivalence class, right? So all parallel lines given to will be like this. So that's another parallel. So I have visualized three different equivalence classes right there. Parallel lines. Infinitely many elements in each. However, if you go with the that actually came up, if you go on the plane, the equivalence class, or rather not all lines, but if we speak of functions that represent linear functions, then we can be more specific and say then slopes are equal. Rather than speaking of being parallel, you can say slopes are equal. So for every real number, there will be an equivalence class of lines with that slope. They are parallel, as we know, and so that is how you can make it specific. That picture is not very specific. It's unclear. First of all, you cannot possibly visualize all the parallel lines. I cannot visualize in each set, and then there are infinitely many possibilities there for angles. But if you go with calculus, well, like pre-calculus, linear algebra ideas, then the parallel lines, what do they have in common? They have the exact same slope. And vice versa. If you have a number, you use it as a slope, you build infinitely many parallel lines with that slope, and they're all parallel. Okay? So every equivalence class then corresponds to a number. Okay? So let me write it here. Equivalence classes, how should I put it? Well, let's say informal are numbers. Okay? Equivalence classes, oops, where am I? Equivalence classes, each equivalence class corresponds to a number, every number corresponds to an equivalence class. Okay? I didn't write it out. Is it clear what I was talking about here? One class is missing, obviously, and that's vertical lines, and so just plus vertical. Vertical lines, for example, is an equivalence class, right? All vertical lines is an equivalence class of parallel lines. All horizontal lines is an equivalence class of lines under this equivalence relation. Okay? So similarly, once again here, the functions, differential functions with the same derivative, it is pretty hard to list. So even though we know the relation between them, all we have to do is just add C. And so you could write an equivalence class of F. This is, well, let me make it specific. So F is equivalence class of F is F plus C, C real. Okay? So once again, making that part specific. So the starting point, as you can see, this is the definition. So we are talking about equivalence of two functions. That doesn't look right. Two functions being equivalent to each other based on what? No, that was okay. Based on what? On whether or not the two derivatives are equal. That's it. So one-on-one relation. And then we want to analyze the whole thing, all possible differential functions, and then we realize that, well, first of all, it is an equivalence relation, and then every function will have its equivalence class. And that is a list of the specific formula for an equivalence class of F. So if there is an F defined on R, as you can see, careful about that, it's defined on the whole real line, then what's the equivalence class? All you have to do is just add constant number. So infinitely many classes, and each one has infinitely many elements in it. Okay, so more equivalence classes. So being a brother, so remember we had a problem with this, whether or not a person is brother to himself, but if you willing to stretch your understanding of that and declare yourself your own brother, which is okay mathematically, it certainly is not a problem really. So what? Then what's the equivalence class of a person? It includes himself and all of his brothers. Of a person meaning male, yeah, and all of his brothers. So. The main thing to note is that it is you cannot have to, according to the theorem that we are now talking about, is that you cannot have this. Two equivalence classes, they either disjoint, case number 1, or they're exactly the same, case number 2. Okay, so let's take another look at this proof. I think these examples that we just considered, I think they suggest already that idea that you cannot have overlaps. So parallel lines, you cannot have two line x is parallel to b, x is parallel to y to z, and then not to expect that x is parallel to z. So that's the transitivity relation that ensures that this is indeed the case. And then we confirm that by proving one abstract theorem about all possible imaginable equivalence relations. And that's what this theorem says. The intersection of two equivalence classes is either an equivalence relation, or it is either empty, or it is the whole set. Okay, whole. Each of the two sets in whole. This is the proof. So we started with the case number one, the negation of case number one. So we said suppose, it's not technically proved by contradiction, because we were not going to end up with a contradiction. We're going to end up with the other case. But we do start with the negation of case number one. So we suppose it is non-empty. There is an intersection. Then the next line, we say let this be A, be an element of that intersection. Next line, that element belongs to one and it belongs to the other, and then that's the definition of the intersection. And then you go to the definition of the equivalence class in the next line and just say A is equivalent to X and Y is equivalent to Y. Okay, so then we conclude that X is equivalent to Y because by the transitivity axiom. Okay, so that doesn't solve the problem just yet, but here below we outline of how the proof finishes. But I think I don't want to leave it this way, and I want to have an actual proof written up carefully. So I'll just call this analysis. And rather, and so that's just how we're going to proceed. But instead, I just go on and write then X is equal to Y by the lemma below. Okay, there is no lemma yet, and usually you refer to a lemma above, but it'll do. So we know what we're supposed to prove. X is equivalent to Y. Okay, and we want to prove that the two equivalence classes coincide. So X equivalent to Y implies that equivalence class of X is equivalent class of Y. You certainly, once again, go back to all of these examples. If this seems too abstract, go to the examples, and you realize that there is no other way to look at it. We just saw it a minute ago right here. As you can see, Y, we discovered that N has the same class as 0, Y, over here. Well, because they are congruent. 0 and N are congruent. That's why they have the same equivalence class. In the next line, N plus 1 is congruent to 1, mod N. So their equivalence classes are the same. And that's what we learned from examples. We want to now to expand that understanding to all equivalence relations. Okay, and that's what theorem does. So you start with examples, you convince yourself that there is some idea that is valuable, and that's how we have this theorem. So in here I just want to finish the proof. It's complicated. We already have an idea right there under analysis. We know how to prove this theorem. Okay, so two parts. Step one, step one, inclusion this. So the assumption is that the X and Y are equivalent, and then to show that two sets are equal, we show that inclusion in one way and then the other. Okay, so how it is done, it's written right there. Okay, so so X equivalent to Y, Y is it the same set? We're not going to prove equality, which is often hard, but instead we're doing inclusion one way and then the other. Okay, one way is right there. So F. This way, F. So suppose B belongs to equivalent set of X, then B is equivalent to X, then B is equivalent to Y by transitivity axiom, right? Okay, are you following this? So by assumption, we pick an element B on the left. We want to show that equivalence class of X is contained in the equivalence class of Y. How? I pick one element on the left. So this is where it is. Okay, and then I want to show that it belongs to the right-hand side, equivalence class of Y. Okay, So we start with x and just write out what we know. B belongs to equivalence class of x, which means that by definition it means that b is equivalent to x. Then b is equivalent to y by the transitivity axiom. Okay, so and then what? B equivalent to y, what does it tell? There are not a lot. That's the advantage of abstract theories and theorems, is that there are not too many moving parts, and whatever can happen is happening right within. It is within like half a page from something that was just defined a minute or a few days ago, but it's here.
Just x is equivalent to y?
No, you're moving backwards. We already know that x is equivalent to y.
Okay.
What can you say about b?
You already said it's part of b, and b is part of x, and it's part of y.
No, that is the conclusion. We only now we can make that conclusion. That's what we're saying here. Let's make sure that this list of or rather chain of conclusions is clear. So like I said, if you know, the challenge usually is to discovering the proof in these situations, and even before that knowing whether your idea or your theorem is correct in the first place. But once you have it, and you know it's true, then what you do is just you pick up either theorems or definitions, and since this is pretty much our first theorem about equivalence relations, you don't have to not luxury, but rather you don't have to bother about finding other theorems to be used. Okay, you know you're going to be used only one thing, and that's definitions. And there are at this point two definitions: equivalence relations, equivalence class. There is nothing else. So whatever you are wondering about what your next step is, well, it's one of the two. So I start with, and I guess this part, idea of proof, qualifies as a method. So proving that two sets are equal is defined in some complicated way, in different way. We prove them by showing that the first is subset of the second, and then second is subset of the first. Okay, so we just demonstrated the first part, right? The first is a subset of the second. So for any b in here, it is also element of that, which means that that's by definition, everything is a definition, pretty much. So which means that the definition, by definition, the equivalence class of x is a subset of equivalence class of y. Okay, at this point, you either just say that it's the same idea, proving backwards, or repeat it. Writing is really easy. So what is the idea of the proof of the second part? It is that replacing x with y, y with x. So you can say it, or you can just write it. Oh, you could actually do it. So I'm going to do it. So I'm writing these two lines on the right, and I will repeat them, switching x with y. Okay, so it can be done quickly. Suppose b is in y, then by definition b is equivalent to y, then b is equivalent to x by a transitivity axiom, then b belongs to x equivalence class, so the equivalence class of y is a subset of equivalence class of x, the end. So technically two different proofs, but it's as you can see, the words are exactly the same, and the conclusion is then is the same. So once again, what might have to repeat itself. So this and that give you this. Inclusion left right, and right into left gives you the equality of two sets. And that is the lemma that we used here to complete our theorem, proof of the theorem, which at this point becomes kind of short. Okay, so read the proof as many times as it takes. Make sure that you understand and just feel comfortable with the proof itself in particular and proofs of this kind in general. So in the meantime, we are moving on to there is an implicit corollary that I have used here from the theorem. That let's make it explicit, and the idea is, as you can see, if you take all the equivalence classes, what's going to happen is that they, like I said, either they overlap or they are equal. So which means that if you take two distinct equivalence classes are what? So it follows from the theorem. Two distinct equivalent classes are, the word I'm looking for is what? Distinct means it's not the same. No, it doesn't mean that they are, so we could have this, right? So two different x and y produces the same set. But that's not what I'm talking about. They're two classes, two sets are not the same. Okay, so if they're not the same, what? No. There is a word for it, disjoint. Yeah. Yeah, disjoint. And then what does it mean if we take all the classes? We take all the classes, so the collection of all equivalence classes on X is, so they're disjoint, and they cover the whole thing. They cover the whole X, right? So remember, X belongs to its own equivalence class, which means that no X is not remains uncovered. Okay, so and they're disjoint. What do we call it? No. There might be many sets, many equivalence classes, and once again they cover the whole thing and they do not overlap with each other. The word for it is yeah.
Can you repeat the question?
Does it start with a C?
No.
Oh, never mind.
The collection of all equivalence classes is what?
I don't know. All real.
No.
Set.
No. Cover the whole thing and they're disjoint. That was the definition.
I couldn't tell.
Like 3 weeks ago, maybe.
I don't understand.
No, does it sound like something familiar?
Well, yeah, I thought it started with a C, but
What? Nobody remembers the word?
I was thinking components, but no, that doesn't make,
I see. It's close. Component. It starts with a P, not a C. You're thinking right. If you emphasize P, that's the key word. It starts with a P. Nobody remembers? What? What? What?
partition.
Partition, yes. Partition, yeah. So remember we talked about, well, odd and even was, in fact, the original example of a partition was odd and even. And odd and even is nothing but the congruent numbers modulo 2. Okay, so the divisible by 2 or remainder is 1. So that's and that they create the original partition. And the definition was disjoint and covering the whole thing. So it's a partition of the set, and then turns out that no matter what equivalence relation you have, it gives you you will have an equivalence class. Okay, so based on our theorem, we conclude indeed that it is a partition. All examples here demonstrate that. But it gives you, even though kind of conclusion is now trivial, and we're using an extra word here, which is might be no more than just a convenience, but actually it gives you a different look at what you might be thinking about when you're thinking about equivalence classes, because equivalence classes is one-on-one relation. Okay, so and then you have to think about one-on-one. Does the brother being a brother, is it an equivalence relation, something like that? But turns out that it is equivalent to just taking your set and splitting it. Well, I haven't proven yet that it is equivalent, but that is the theorem that actually, once you start thinking this way, you're starting thinking about the converse. So the collection of all equivalence classes is a partition. What is the converse? Even though there is no then, what would be the converse? Or if you don't like converse word, which is not entirely applicable here, how about vice versa? The collection of all equivalence classes on X is a partition, and vice versa. What does vice versa mean?
So would you say a partition is the collection of all equivalent classes on X?
Yes, yes. So conversely, any partition of X is a collection of all equivalence classes of a certain equivalence relation on X. So that is a vice versa. That's not the same direction, right? These two statements are not equivalent. One, and then the other one is the converse. So in other words, we demonstrate that if we have an equivalence relation, then going through those two steps, we create a partition. So from equivalence relations to partition like this. And now backwards, if we have a partition, where is an equivalence relation? We have to create it now. Now, proof is not uncomplicated as soon as you realize what the partition, what the equivalence relation is. So let's suppose it doesn't have to be infinite, but finite. But let's suppose it is finite. X1 xn is a partition of X. Okay, so the picture is on the right. Okay, can you think of an equivalence relation? Define X is equivalent to Y if you have nothing. You have numbers, you don't have numbers, you don't have functions, nothing. All you have set X and a partition. X1, X2, X3, Xn. What equivalence relation would you suggest? Well, remember where we came from. We came from equivalence classes. So I need to create an equivalence relation that would produce this partition as a set of equivalence classes. Well, I'm not sure if it is. How easy to jump to the conclusion, but actually the conclusion is very easy. Not the conclusion, but rather the idea is you will see as a straightforward shortly. Okay, so always saying that the two elements X and Y are equivalent when they belong to one element of the partition. The end. So once again, there is nothing but a partition of the set X, okay? And then we're defining an equivalence relation based on that partition in that manner. So X and Y are equivalent to each other when they belong to the same element of the partition.
How are they equivalent?
What?
How are they equivalent?
How?
Yeah.
No, that's how. How do I know? You know, what is an equivalence relation? Or just any relation. You have two elements, you verify, and you ask yourself, are they related or not? That's how you verify it. You have two elements, X and Y. What do I do with them? I go to my partition and see, do they belong to the same set, same partition set? If they do, they are related. If not, they are not.
Like if that partition set was like odd numbers, and you had 3 and 9,
Yeah.
they're not equivalent, right? But they're still in the same odd numbers.
So partition is in odd, even in odd numbers, okay, and you pick nothing else, so we're not talking about divisibility, just say one set is even, the other set is odd, okay, so then I declare an equivalence relation. I say that two numbers are equivalent when they belong to either one or the other set. So then you can see then either X will be equivalent to Y either when they're both odd or when they're both even. And indeed, it would make a full circle back to divisibility by 2. Right? So,
Yeah, but like if you pick 3 and 9, they're not
Yeah.
equivalent.
they are equivalent, but by our declaration they are. Because the equivalence class is odd numbers, and they belong to the same class, right? So they are equivalent. Right?
They're equivalent, but they're not equal.
No, they're not supposed to be equal. Equal is what we're trying to move away from. We are sort of expanding the idea of things being equal to the idea of them being equivalent in some sense. So they are not the same necessarily, but they are equivalent in some sense. And whatever that equivalency, how can we relax the idea of two things being equal to each other in such a way that they are still meaningful and we can draw conclusions? And those 3 axioms give us that, especially the transitivity. Okay, so, and that brings me to the part of the proof that is crucial, what's supposed to follow. This statement, I define the equivalence relation. I'm supposed to do next what? I got to demonstrate that it's an equivalence relation. Right, so I say that it is, by only using this wiggle between X and Y. Now, is it an equivalence relation? So I have to go do 3 axioms and demonstrate that it is indeed an equivalence relation. So axiom 1, reflexivity, is X equivalent to X? Let's carefully do one by one. So why is X equivalent to X?
Because it's X, and that's X, so...
No, look at the definition, right? We will be referring to this part again and again, or rather not again, 3 times. So why is X equivalent to X?
X belongs to xk and X belongs to x.
That's right. That's it. I mean, it sounds kind of silly, but really, that's inevitable sometimes. So X belongs to xk, and X belongs to xk. Okay.
So where do we get xk from? Like, who came
It is a partition. The partition is where it came from. So this is collection x1, xn is a partition. It doesn't have to be finite, but let's just keep it simple. Or not. You gotta put ... there, and you see it doesn't have to be finite. And I just decided to list the elements of the partition.
Gotcha.
Okay. So number 2, symmetry. X equivalent to Y supposed to imply that Y equivalent to X. Well, there is no, as you can see in the definition I underlined with blue, there is no order X followed by Y, Y followed by X, the same thing. So naturally, XY belongs to XK, or YX belongs to XK. It's the same statement pretty much, or exactly the same statement, right? So there is nothing to prove. The third one requires a little bit. X equivalent to Y and Y equivalent to Z. Why does it imply that X is equivalent to Z?
Where did Z come from?
Well, that's the transitivity axiom, remember?
Oh, yeah.
Now we're proving it.
Yeah.
So reflexivity, symmetry, and transitivity right here. Okay.
The point of those 3 was to prove the definition, isn't it? The defined part.
Yeah, we are proving the definition, yes. We're proving that whatever we define, we did it a few times, right? Every time we had an example and we declared that this is an equivalence relation, we had to go through 3 axioms and demonstrate that they're satisfied. It is the same thing only on the abstract level, because all we have is the partition.
Yeah, but number 2, all we did was restate the definition to prove.
Because it's so simple, then it is, you feel kind of silly to actually trying to explain it. I mean, the second one, right? So x and y belongs to ak, or y and x belong to xk. What's the difference? There is no difference.
Yeah, but we're using the definition to define to prove the definition.
I don't follow.
Like, we're doing those 3 steps to
Yeah.
prove the definition, right?
Yeah.
But then we're using it in those steps, so how's that? It's just a circle. We're not really proving anything.
No, I don't think so.
Aren't we?
We're only using that blue part. That's the only thing that we're using. As a definition, it is an explanation of what that wiggle means. So even though it appears that is a statement to be proven, I didn't write all the words, but we need to prove this statement over here. Or under what circumstances we know that x and y or z are just elements of the set x, and the meaning of the wiggle is explained right above. Okay, so y x wiggle y and y wiggle x implies that x wiggles z, that we need to demonstrate. So how do we prove it? Well, there's no trick. The definition, that blue, underlined blue, is what you have. And then just write the definition and let me try it. So x equivalent to y means we already have it exactly. xy belongs to xk for some k. Okay, the second statement, forget about the previous ones, and let's just write it entirely apart. Y equivalent to z means that yz belongs to x sub m for some m. And thirdly, xz belongs to some x p for some p. Okay, so that's all. So and now we have the first statement plus the second statement supposed to imply the third statement. Do you see how?
So does y belong to xp or no?
Well, that if it did, we would be good.
And that's like the same thing for saying, does x belong to xm?
Right. So,
Wait, so does z belong to xk?
yes,
Wow.
but we have to prove it. It does. I mean, look at the picture at the top.
By the definition of a partition, that says they don't overlap, right?
Exactly.
They have
So
to be equal.
take the. That's right. But that's pretty much it. That's pretty much it. So you look at the these 2 statements, and from the disjointness of the elements of the partition, this cannot be 2 different sets, because they have a point in common. That point is y, right? So these have y in common. So they are the same. Same, in other words, k is equal to m. Okay, and then well, if you look at it, then the last step is x belongs to xm and y and z belongs to xm. Right? I'm just reading it. Once I know that k is equal to m, it's the same number. I just take a statement about x, take a statement about z, and just write it out, and so we're back here. Okay, so challenges obviously you're facing here, and so just think about it.